Hello, Mr. Aaron, Mr. Rana, right?
Yeah.
Okay, so binary tree, right? Binary search tree. Do you still remember?
Yeah. Oh, in your office.
Yeah. Okay, so this is the binary tree, also binary search tree, because the left nodes are smaller than the root, than the parent. The right nodes are strictly bigger than the parent. Okay, this is a valid binary search tree. Let's look at these as well. Yeah.
That one is going to be invalid. 1.5. Yeah, that no, you're going to write is going to be invalid.
No, I'm not going to write for that's a -1.
That's invalid.
Why is it invalid?
Because it's on the right. Still on the right side. Because it's bigger than 1.
Yeah, this one.
Is less than 1.
Yeah, but even this node is smaller than 2, but it's bigger than 1, which is not right. Okay.
No, it's less than 1.
It's less than 1, so this is invalid. So what's the most important thing about this binary search tree?
Is that we can put it in order and it will be in order.
That's right. If we perform an in order, so basically we visit the left tree first and the current node and the right tree, that will give us an in order. Okay.
Here, we can see your shadow.
That's fine. Okay, so let's look at a simple binary search tree, which is 0, 1, 2, 3, 4 nodes. So is this a binary search tree? Is this a binary search tree? Yes?
0, 1, 2, 3.
Yeah, it's a linked list, it's also binary search, but what's different? What's so special about
It's
it?
one line.
One line. So is it a good binary search tree?
It's imbalanced.
It's imbalance. Yes, all I'm talking about is imbalance. What's balance? Balance is a balanced tree. A balanced binary tree is that the difference of the left tree and the right tree for any node should be no more than 1. Okay, but for this one, it's an imbalance because look at this node. The left tree, the distance, the depth is 0. The right is 1, 2, 3. 3 minus 0 is more than 1. This is imbalance. But in the meantime, if we put a 1 here, 0, 2, 3, this is balance. Okay, this is balance because look, this is 1, this is 2. 2 minus 1, no more than 1, right? The difference no more than 1 is 1. Okay, make sense? This is the balance. Also, what can we do? 2, 1, 0, 3, right? This is also a balanced binary search tree, right? All 1, 2, 3, all these 3 are binary search tree. This is not balanced. This is balanced. This is balanced.
What if the 1 has another?
What do you mean?
What if the 1 here?
You mean what do we put here?
No.
Okay, you mean 1.5, right?
Yeah. Is it
Yes, it's a binary. Yeah, for any node. Look, the difference. Left one is the same.
Yeah, I'm saying you're talking about the 2 minus 1.
Any questions so far for the?
Isn't that 3 and because you were talking about the 2 minus 1 thing.
The difference, the absolute difference. Left
What's
is smaller.
What's the difference in that one?
This one, yeah.
In that
Okay,
tree?
let's look at this node. The left tree, the depth is 1, 2. The right tree is 1.
Oh.
Yeah. So for every node, okay. But for this one, look, the difference. The left is 0. The right is 1, 2, 3. 3 minus 0 is bigger than 1. That's what I'm saying. The depths of the left tree and the right tree for every node. Okay. Every node. Why do we prefer? Do you know we prefer the balance over imbalance? Why?
Because the imbalance is usually the worst cases.
Why? In worst case, in what?
In some problems.
Some problem. What kind of problem? What do we need a binary search tree for?
Putting things in order to find the solution.
To find. For example, if I want to find the 2 here, so there's only one way I can go, right? Yeah. Find 2 or 3. In the worst case, I need to travel n. Am I right? There's only one way. So basically, it's linear search. We are not making use of the binary search property. But for this one, if I want to look for number 2, right? Balance. I don't need to look for anything here, right? Then there could be a very big number of nodes on the left tree. So at each step, I can abandon almost half of it by search.
But what if there's nothing on the left side?
Then this, look.
Yeah.
That's what I'm saying. This is imbalance. For imbalanced tree, if we perform a search, it will be degraded into a linear search, because we are not making use of the property that the left trees are smaller, the big trees are bigger.
Basically one line.
That's right. Yes. Okay. So we given a binary search tree. We want to make it a balance. You can. I mean, obviously, look. There are more than one balanced version of the same binary search tree, right? So you can return any of it. Okay, so for example, we're given any binary search tree, we want to make it balanced. Okay? So any idea? So if we're given this, any binary search tree, okay, we're given any binary search tree. We're given a binary search tree, we want to balance it. We want to make a balanced version of it. And because there are more than one, there are more than one usually. There could be more than one. There could be more than one balanced version of this same BST. We can just return any of them. What I mean by the same version is that if we perform an in-order, we get the same sorted list, right? If we perform an in-order, we get the sorted list. Okay, that's a hint. So how can we do it? Any idea?
So left, no, right.
Yes. What's this? The left, no, right. What are we doing there?
It's in order.
Okay, so we can make an in order of the BST, then we got a sorted list. Am I right? That's the first step, right? So for example, like this one, we have a sorted list 1, 2, 3, 4, 5, 6, 7. So how do we make a balanced binary search tree out of it? So which node should be in the root node? If we want to make a balance, so which node should be the root?
4.
4. Yes, we choose the middle, right? For example, like, yeah, we can get this sorted list, right? By performing an in order of any binary search tree, we get a sorted list, and then we pick the middle as a root, right? So okay, 4. So what nodes are on the left? What nodes are on the right? What nodes are on the left? What nodes are on the right?
1, 2, 3 is on the left, and 5, 6, 7 is on the right.
That's right. Yes. So 1, 2, 3 is here, right? That's 1, 2, 3 here. 5, 6, 7 is here, right?
Yeah. So
okay, and then
4 to 6, and then the 6 is 5 and 7.
Yeah. Okay. Okay. So now look, what's this? Look, we pick the root node, and then these nodes are on the left. These nodes are on the right. So we can continue working out on this subprogram, right? So for 1, 2, 3, this is sorted. What node should be in the middle?
So 4 should be connected to 2.
Yes. So 2 should be in the middle, right? Okay. So what's that?
1.
What's that?
3.
Oh, what's right? Okay, 3. Okay, and this one as well. So we pick 6. And 5 and 7. Okay, so this is the recursive program, recursion, right? Every time we pick in the middle, the left is the left tree, the right is the right tree, and we continue dividing this subprogram until we get only one node. If it's one node, we don't need to divide anymore, am I right? Yeah?
Yeah.
If it's a one node, we just return it, okay? So the in-order thing, let's do the in-order thing first, and then we do this. Then the next step is to build it using the recursion, okay? So we talk about this in-order thing many times. We can do it many ways. The recursion is the way to go, and we can use the iterator, right? Define depth first search, the root, if not root, then return. Okay, and then yield from, right? We talked about that in previous lesson. Yield from DFS root.left. Right? We visit the left tree first, then yield. Remember this yield keyword? I promise you to give you £5 every month. I promise you to give you £5 at the end of every month. Yield root of value. Okay? And then what's next? We visit the left tree, we visit the current node, what's next? Look, this is the root. We visit the root.left here, the yield.root.left, because there could be a many, so we yield from here. Yield from. Okay, we yield from this place, yield this value, and what's next?
dot right.
Yes from root of right, okay? So yes from DFS root of right, okay? We can do it by inserting. So if we have this array here, we can inserting. Instead of year from, we can say array.append. We can depth search root of left and then array.append root of value and depth search root of right. Okay, this is syntax, much cleaner syntax, sugar. Okay, then with this depth search, now we can array equals we converted because it's an iterator, we converted to a list depth search. Now we have sorted this. Now we want to construct the binary search tree, balanced binary search tree, using this approach, recursion, using this approach, okay? So how do we do it? Using recursion. Define, let's say F, or we say build tree, okay? Build tree. Build binary search tree, BST. So we want to build it here. We need to give a left or right pointer, right? Left or right pointer. If the left is bigger than right, then we just return because there's no point, right? Left or right pointer. We use the left or right pointer, right? The left at the beginning, we put it here, right here. If L equal R, if there's only one node, then we just return, right? Return 3 node.
What if there's an even number?
Value. Okay. What do you mean?
What if it's an even number? For example, if it's 8 and then there's no center.
Okay, so that's a very good point. Okay, so if there's 8, there's no center. You can pick 4 or 5. It doesn't matter as long as it's balanced, right? We can prove that by choosing the middle one, either it's this one or that one, it gives us the optimum. Right? Because the balance tree is that the difference is no more than 1, okay? Now, if there's only one node, then we just return of it, right? Otherwise, root equals 3 node. We want to get the middle, right? The middle one is what? The middle one is left plus right divided by 2, right? Or shifted 1 position. Alright? The middle one. How do you get the middle? L plus R divided by 2. Alright?
Yes.
Okay, the middle one. 3 node root array middle one dot value. Now we want to build the left tree, right? Root dot left equals build tree. Now the left bit, okay, look, this is the middle, right?
Yeah.
This is the middle. Now this middle is root. Now the left tree is root dot left equals build tree recursion, right? The left will be L middle minus 1, right? Yeah? Look, root dot right equals what? Root of y equals build tree. What's the index I should give it? This one is n plus 1, middle plus 1, up to r. Okay, and then return root. Okay, you see? Using the recursion, 2 recursions. The left recursion is to perform an inorder on a binary search tree, and we get the array, sorted array. The right recursion, we are building a binary search tree, balanced binary search tree by following the strategy, always pick the middle as the root. Once we pick the middle, we know the left, the numbers on the left. We know the numbers on the right, and we recursive build it. Yeah. If there's only one root, then we just return the leaf node. This is the leaf node. Otherwise, we get the middle. And the left part, we're using the recursion to build it. The right part, we're using the recursion to rebuild it, and we return root. Okay. Okay. Any questions so far?
No.
Okay. So what have you learned today?
We learned about binary.
Can you just present this the solution here, just like that? Come on, quickly. Bonus, 5 minutes.
We
You can too. You too
we
can.
need binary. We have a binary.
Come on.
We.
Demonstrate on the whiteboard. Come on. Yeah, 5 minutes.
Me.
Yeah, both. You two can work as a
We
team.
have a binary search tree. Balance.
I mean, you can. There are 2. You can both present 1. Okay.
So we have a binary search tree, and so first of all, we wanna make it balanced, not imbalanced.
That's right.
Imbalance is when the depth of the left or the right tree is more over 1.
Distance, the depth.
Yeah, that's what I just said.
Okay.
And then, so we use those like numbers.
Yeah.
Here we do 2 pointer, and then we close the count until they're the same. Until they meet, like in the center, or if it's even number, and then you can choose the left or right if there's no center. Yeah, you get a chunk to the left side and get a chunk to the right side. Yeah, and yeah.
What were you drawing? That was interesting. Can you say?
A tiny binary tree.
Okay, so can you say in 1 or 2 sentences, 2 or 3 sentences, what are we doing today?
We have a binary and we want to make it balanced.
Wow, that's very concise. Yes, that's what we're doing here. What kind of strategy are we using to build a balanced binary search tree?
We just use computer.
Okay, so write it. Yeah. So the solution is that because it's a binary search tree, we perform an Inorder. We get the sorted list, right? Yeah. Do you understand this part?
Yeah.
Now with the sorted list, then every time we pick the one in the middle as the root. So look, 1, 2, 3, 4, 5, 6, 7. We pick the 4 as the root, and 1, 2, 3 should be on the left side. 5, 6, 7 should be on the right side, right? And for the left tree and right tree, 1, 2, 3. For 1, 2, 3, the 2 should be in the middle, right? So 2 should be in the middle, 1 should be in the right, left, and 3 should be in the right. So we can recursively divide this problem into the sub-problem. Do you get it? And this way we can build a balanced binary search tree. Okay? Good job. That's it for today. Bye-bye.
Bye. Bye. Bye.